Hey students, I thought I'd make a solution here. Let's see. This one is on our induction. It says two long parallel wires carry equal current in opposite direction. The radius of each wire is A, and the distance between their centers is D. So it would look something like this. We've got this wire, and it has a, I guess I didn't leave quite as much size. Let me make it a little bigger. And here is our radius A, okay. And then there's a second wire. Maybe I'll put it here. It too has a radius of A, but their centers are separated by D. But see, the idea of the problem is to find the inductance. Let's see, the radius of each wire is A. Okay, show that if the magnetic flux within the wires themselves can be ignored, the self-inductance per unit length of L, so in other words, depending on how long these wires are, is given by this formula. And then it gives us a fun little hint here that if we can figure out the flux, and so the flux is the magnetic field times the area times the angle between them. And here's where we have a little bit of work to do, because we've learned here that for a single wire, and this is how I want to attack it for this one here, let's go ahead and ignore the second wire for a moment. Let's just find out how much flux we get from the edge of the wire, I'll call the wire, this first wire, to this edge of the second wire. And so as measured from the center of this wire, this position would be D minus A. And the reason that's important is we learned that the flux from a single wire depends upon this R. How far away are you? And so why don't I redraw this? Why don't I draw this to look something like this? That, okay, I have this wire, and I'm kind of curious then, how much flux is there from the edge of the wire, so that would be position A, to where the second wire is going to be. So let me just ignore the second wire for a moment. But the second wire then would start at D minus A. And so if we go back a chapter or two and we do our right-hand rule and we kind of pretend that maybe the current is heading in this direction, then the magnetic flux would be coming out, and it would kind of fill this space. And so if we made kind of a rectangle here, and we make the rectangle of length L, and we say, okay, well, how much magnetic flux is there? We would have to do something along these lines. We'd say the flux is, and it would kind of be this summation of the strength of the field times the area times cosine of the angle. Now, there's a lot to unpack here. The first part is that because of this, because the magnetic field decreases with your distance away from the wire, and R is that distance away. And so if here's the center of the wire, then we would get maybe right about here and start our calculation. This R is going to start at a small value of A and keep getting bigger and bigger and bigger. And so in other words, this value changes. That is, the field is strong when we're next to the wire and then gets weaker and weaker and weaker. And so we need to then maybe chop this into little rectangles, if you will, and add up the flux from each rectangle. And so the first thing to unpack is to say, I'm going to then take the flux for a single rectangle and then add a whole stack here of rectangles until I get the total flux. So this is going to become an integral, or maybe before I even make it an integral, I might say it's going to be a summation where I have a magnetic field of this strength and the area of this rectangle is its length L, and then in this picture you might say its height. I don't know what you want to call this, a delta, you might call it Y because we're in the vertical direction. But R might be more appropriate since we've got the field in terms of R. It's how far away you are from it. Because we don't have to be adding the flux along a vertical way. We could have doing it like towards the camera adding, or even at an angle off of here. It's just, we're just adding up radially outward. So I would call this then a dr. And then this would be then the limit as the dr goes to 0, as we're making it smaller and smaller and smaller. And so that's the part that I said we got a lot of unpacking to do, because we really have to then change this into a infinite summation, an integral. And so this integral symbol is what we get when we take the limit. This is the second fundamental theorem of calculus here. So this would be mu naught I over 2 pi r L, and then the dr. Now, one more thing to unpack is this angle. Now, fortunately, the angle is just 0 degrees here, because the rectangle I'm making, the normal vector, you can kind of put your fist on it, would be pointing, towards the screen there. And then, of course, the right-hand rule for the magnetic field, I'd point my thumb this way and the flux would circle around, and again it would come out towards the screen. So both the normal vector and the magnetic field are going towards the screen, and so that's why I have this cosine of 0, which is just 1. So maybe I'll put that in my little equation here. And then, as we mentioned earlier, I'd be adding the flux from the edge of the first wire to the edge of the second wire. And then, of course, maybe one more statement, which I'll make down here at the bottom. The total flux, then, is twice the flux we would get from just one wire. See, this whole calculation would be repeated if I said, okay, well then, what about the second wire? How much flux do you get from it? And it would be the same value. Now, just to be clear, I'll put that second wire and put the current, as they said, in the opposite direction. So this is what we call twin lead wire, 2 wires side by side. And what's interesting here is if you had it in the opposite direction, using the right-hand rule for the direction of the magnetic field, the lower wire would make flux come in the same direction in this area, because now this area would be above the second wire, and so the flux would be coming out. And so actually 2 wires that were in the same direction, the flux would cancel, but in opposite direction. And this is common for sending data. You'll have a little, power cord, USB on your phone or something, and you are connecting data between your phone and your computer. You send information down this little wire and it comes back. And so those little, white charging wires that you're probably familiar with if you have an iPhone, it's got that little lightning plug, are a bit more complicated than this. If they were just like this, you would have induction, and that would slow down the data rate. Because remember, the induction is kind of an impediment to making the current go down. And so you wouldn't want this. You want to get, rid of this. This is why they take those wires and they twist them. They take the wire and then they twist it and then they twist it and they twist it. And so it's a twin lead twisted wire to eliminate that induction. Otherwise they and then they do some other fancy things too. But just twisting it makes an enormous amount of difference in how fast you can send data down them. So, like I said, we wouldn't want that induction. Now, sometimes you want induction, so it really depends on what you're trying to get. But in this case, we're just asked to find how much duction would you get from a set of twin lead wires. Anyways, but that's why this factor of 2 goes in here, because we need to then double it to get the total flux from both wires. Now, let me just put the limits on here again, because fortunately that was the hard part right here. This is the hard stuff, knowing that you have to take our flux calculation, turn it into an integral, pay close attention to the angle and close attention to the limits and double it and all that, because the actual integral itself is pretty straightforward. Like any integral, you kind of want to focus on what are constants and then pull all of those out. And in this case, you're going to be just left with the dr over r. And so that's kind of what you're adding up. And again, just kind of showing you in the picture, you're adding up these little drs. You're adding up the slices of the rectangle. And then, of course, that rectangle is measured its magnetic field in terms of R. And so that's why we have set this up as a dr, just to say how far away are we from the wire. And then the 2 cancels off there, so that makes it a little bit easier. Let's see. And then now we just have ln of r when we do our integrals from a to d minus a, which I think this pretty much finishes up the problem, because then I'm going to get an ln of d over a. In fact, maybe I should write it as ln of d minus a minus ln of a, and then take advantage of the property of logarithms that I can write that as a quotient. And now to finish the problem, they say the inductance is just going to be the number of turns you have. And if you just have, this one rectangle, n is equal to 1, times the flux we just calculated. And then this little formula says then divided by the current. So that goes away. And now we finish with just a mu naught L over pi times ln of. And I believe that matches. Yes, it does. Good. And so, ta-da, there's our calculation. So, good. Hope that helped in some way. Take care.